Hello, game theorists. So we just finished playing our 3x2 game. I think all of our row players said they want to play U with probability 2/3 and D with probability 1/3. Our column players, though, didn't always agree on how to mix between L, M, and R. So let's see how this game should work. So you can quickly verify, look at the payoff table here, that there are no pure strategy Nash equilibria. That means both players will want to randomize, they'll want to use a mixed strategy. So let's try to find out what the best mixed strategy should be for each. So let's see. Let's say our row player plays U with probability A, and they play D with probability 1 minus A. Our column player plays L with probability X, and they play M with probability Y. And they play R with probability 1 minus X minus Y. So as you know from our videos, what we do is we find the expected payoff for each player. Then we take partial derivatives, set them equal to 0 in order to maximize. All right, so expected payoff for our row player. So they get 1 with probability A times X, 0 with probability A times Y. So to make the game tractable, I put a lot of 0 zeros in there so the math won't get too out of hand. And we get 2 with probability A times 1 minus X minus Y. We get 0 with probability 1 minus A times X. Three with probability 1 minus A times Y. And 0 with probability 1 minus A times 1 minus X minus Y. So all our stuff with zeros just cancels. So we're left with, well, 1 times AX is just AX. So one thing to think about as a practical measure, should I simplify this first with algebra and then take derivatives, or should I take derivatives first? Ultimately, though, it doesn't actually matter. You should get the same answer either way as long as you don't make any math mistakes. I think I've done it both ways in some of the class videos. If I had to pick, though, it might be a little bit faster to do the derivatives first and then simplify, because when we take derivatives, some things just go away, they just go to 0. So that might speed you up a little bit, but it doesn't really matter. You should get the same answer either way. So our row player controls either U or D, so they're controlling A. So you take the partial derivative with respect to A. So A times X, when taking a derivative with respect to A, that'll be just X. And this over here, the a is going to go away. You're left with 2 times 1 minus x minus y. And this one is, that expands to 3y minus 3ay. But the derivative with respect to a, that's treated like a constant, so that just goes away, and you get minus 3y. So that's our condition for the row player. Now let's look at things from the column player's perspective. So first we write down the column player's expected payoff. So they get minus 3 if we're over here. That happens with probability a times x. We get 0 with probably 1 minus a times x, but the 0 is going to cancel everything, so we'll ignore that. We get 0 over here, so we can, with probably a times y, so we ignore that as well. And then we get minus 2 down here. Minus 2 with probably 1 minus a times y. We get minus 1 with probability a times 1 minus x minus y. So that's our expected payoff. So our column player decides we're playing L, M, or R, so they're picking the probabilities x and y. So we want to pick those probabilities in the way it's going to maximize their expected payoff. So to maximize, we, as usual, take partial derivatives and set them equal to 0. So we take one partial derivative with respect to x, and then another partial derivative with respect to y. So the partial derivative of minus 3ax with respect to x is just minus 3a. This term doesn't have any x's in it, so that just all goes to 0. So you can see I saved a little bit of time by not expanding this term because it all just goes away. I didn't have to worry about doing the algebra, expand, and simplifying. Let's see, this term here does have an x, so it's a minus x times minus a, so that should come out to plus a. So we simplify a bit, that's going to give us, we have minus 2a equals 0. Which means a had better equal 0. All right, now we take our partial derivative with respect to y. So this term doesn't have any y, so that's all going to be 0 in partial derivative land. This one does have a y. So the y is going to go away. And we're left with minus 2 times 1 minus a. See over here we have a minus y times a minus a, which will be a plus ay. When taking the derivative with respect to y, that's going to be just a plus a. And all that is set equal to 0. So now we got to expand this. We have a minus 2 plus 2a plus a is 0. And then we combine those to get 3a. I can push this minus 2 to the other side. 3a equals 2, which gives us a equals 2/3. So now we get to the point that I talked about in some of the videos. We saw that we have these 3x2 games, and you get these apparently contradictory conditions. So one condition says A has to be 0. The other condition says A has to be 2/3. They clearly can't both be true. So here's how we dealt with that. If you recall from the videos, we can use this condition here and set the other one, set y equal to 0. Alternatively, we can use this condition and set x equal to 0. We solve both of those cases and we look at the results. So you might get two equilibria, one equilibrium for each case, or you might get only one equilibrium because sometimes one case leads to something that's impossible. So let's go check that. So let's keep this condition here. So we're going to use this condition. We're dropping the other one, which means we got to set y equal to 0 if we're dropping the y condition. So what does that imply? Well, let's plug that y equals 0 condition in over here and see what happens. We could get a value for x, or it could get something impossible, which means case 1 doesn't work. So we just got to go through the math and see what happens. So we get x plus 2 times 1 minus x minus y, but y is set as 0 here in this case, plus 3 times 1 minus a times y, but again y is 0. Or excuse me, 3y. Well, it doesn't really matter because y is 0, so it's going to cancel out anyways. And that should be a minus 3y. So you have x plus 2 times 1 minus x minus y, but y is 0, minus 3 by but y is 0, so minus 3 times 0. All right, so this goes away, and we have x plus 2 times 1 minus x equals 0. Expand that, x plus 2 minus 2x is 0, which gives us 2 minus x is 0, which means that x is 2. Well, that can't be right. X is a probability. Probabilities can't be outside the 0 to 1 range. You can't play X or play L with probability 200%. So that rules out case 1. This doesn't work. So if case 1 leads to something impossible, we got to turn to case 2. So case 1 came from using this constraint. Now we're going to use the other one. So we're using this constraint for y. We're dropping this one, so we're saying x equal to 0. So again, if you're dropping this constraint, you have to set that variable, in this case x, equal to 0. So I plugged this case into that rule I had for the row player, and see what pops out. We might get something logical, we might get something that's impossible, and that'll tell us how to proceed. So if x is 0, then we get 0 plus 2 times 1 minus x, but x is 0, minus y. We have to solve for y, so that's going to stay. Minus 3 times y is 0. So that just goes away, and we expand this, we get 2 minus 2y minus 3y is 0. 2 minus 5y is 0. Push that 5y to the other side, 2 equals 5 times y, which means y is 2 over 5. 2 over 5 is in that 0 to 1 range, so that is a valid probability. So that one works. So now, just to be formal, I'll route the Nash equilibrium. So remember, if you're answering a test question, just saying y equals 2/3, that's not the Nash equilibrium. For starters, you gotta specify your full strategy, the probabilities for all the variables, and second, you gotta tell me what y means. So here's what the Nash equilibrium should look like. So in this case, A was 2/3, and A was the probability of playing U. So our row player plays U with probability 2/3, which means they play the other option, D, with probability 1/3. For our column player, we said x is 0 in the only case that worked, and x corresponds to probability of playing L. So M is play with probability y, and we just demonstrated that y should be 2/5. And that leaves R. Probabilities have to sum to 1, so this will probably 0, and this will probably 2/5. The last one must be played with probability 3/5. So that's our Nash equilibrium. Hope that gave you some practice in working with 3x2 games. Chapter 7 is a kind of difficult chapter. That's why I had a couple of games based on it to give you some opportunities to test out your skills. I can put 3x2 games and even 3x3 games on the exam. It's definitely a question that could occur. If I do that, though, it'll probably be something like this where it's got a bunch of 0 in there so the math doesn't get out of hand. So that's all I have for today. Take care and stay safe out there.